Okay, hello and welcome back. In this video we're covering 4.3, which is on solving systems of two linear equations using another technique called the elimination method. So previously we've used something called the substitution method, so we'll see a different approach throughout this section. So let's just jump right into it. So we're going to solve a linear system, and specifically a system of two linear equations using this method. And so we have our similar setup here, where we have two linear equations, and we want to try to solve, essentially we're solving for their points of intersection, or we're finding the values of x and y that solve both of the equations simultaneously. And with substitution, we solved maybe one of these equations. We could solve it for x, and then go back and plug that in for x in the other equation. But we can take a different approach called elimination. So let me write out the two equations a little bit bigger here. We have x plus y equals 11 and x minus y equals negative 5. So what we can do is add two equations together. And it might feel a little bit weird at first, but let's do that here. So let's imagine this is like a regular addition problem. And the way I'll do this is, the first task is to line everything up like this, where we have our x's, our y's, and then the constant numbers on the other side. So it's in um, standard format. And I'm going to add the x's together. So looking at like this column, I'm going to add those together. X plus x will give me 2x. I'll do the same for my y's. So looking at this column, I have positive y plus negative y. So I'm adding these two equations together. Well, notice that will give me 0y. They're going to cancel out. And then I'll add my third column. I have 11 minus 5. So that will give us a positive 6. So we had 0y. So the y is eliminated. And that's the kind of situation that we want to put ourselves in, where when we add the two equations together, one of the variables will cancel out and be eliminated from our equation. So then we're just left with 2x equals 6. Then I can divide both sides by 2. 6 divided by 2 is positive 3. So we have it solved already for one of our variables. You know that x equals 3. So I can go back and plug this into either of the two original equations. Let's jump up here. I'll pick that first equation, x plus y equals 11. Let's substitute in 3 for x. So 3 plus y equals 11, and subtract the 3 over. So y will equal 8, and we get our y value. So our solution to the system, or the point of intersection of these two lines, will be 3, 8. 3 for x, 8 for y. So just to recap, and this one was pretty much set up for us. We'll see with some further examples that we might have to do a little bit of manipulation in order to get this set up. But we want to get something like this, where when we add the two equations together, one of the variables is eliminated, and you're able to solve for whatever remains. Then you can go back and plug that value in to one of the original equations and find the value of your other variable. And again, this one was set up very nicely for us. We could just go through and everything eliminated very easily. But let's see when it gets slightly more complicated. So example 2, let me write these out. We have 2x plus 5y equals 5. Then we have x plus 4y equals 7. And we want to take the same approach. We want to solve this via elimination. And what I want is like what we had previously, where we basically have the positive and negative version of a variable. And it could have a number in front of it as long as one of them is the positive version and one is the negative version. So that when we add them together, they will cancel out, as we saw in example 1. So we don't quite have that for example 2, but what we can do is multiply one or both of the equations by some number in order to kind of like force that situation to happen. So if I look at my second equation, I have this x on its own, and then I have 2x in that position in the first equation. So it would be nice if there was a negative 2 in front of that x, so that when I add them together, they will cancel out to 0. So let's try to make that happen. I can multiply the entire second equation by negative 2. So I can't just do it to the x alone. I have to multiply every term by that negative 2. So let's rewrite the system. I'll keep the first equation the same. 2x plus 5y equals 5. And then we'll multiply every term in the second equation by negative 2. So I'll get negative 2x minus 8y, because 4 times negative 2 will give us the minus 8. And then also we need to do this also to the other side. So 7 times negative 2 will be negative 14. So we've just scaled the second equation by multiplying everything by some number. Now let's add these together. So 2x minus 2x will give us 0x. That's what we want. We've eliminated the x's. And then we'll have 5y plus negative 8y, or 5y minus 8y. That should leave minus 3, minus 3y. And then we have 5 plus negative 14, or 5 minus 14. So that should give us a negative 9. So we basically have negative 3y equals negative 9. Let's just divide both sides by negative 3. So y will equal positive 3. So we got one part of our solution. Now let's take this value and go and plug it into one of the original equations. So I'll take the first equation again. 2x plus 5y equals positive 5. So let's plug in 3 for y. So I've got 2x plus 5 times 3 equals 5. 5 times 3 is 15. So let's subtract the 15 over. So 2x will equal negative 10. 5 minus 15. And then let's divide both sides by 2. So negative 10 divided by 2 is negative 5. So that will be our second part. So our solution, our x value is negative 5, and our y value is positive 3. So here we had to do a little bit of modification first. We had this initial first step of multiplying one of the equations by some number. We might have to do that to both, and I think we'll see an example of that. So first we altered our equations, kind of like rewrote them, and then we added them together, and we saw the cancellation of one of our variables, which is what we want. Then we get our first part of our solution, then go in and plug it in to one of the original equations and get your second part. So we could also be solving these by substitution, but it's good to know both of these strategies because sometimes one might be a little bit easier to do than the other, depending on our starting situation. All right, let's look at another example where we might have to modify both of our equations. So we're starting here with 2x equals 9y plus 4, and then we have 3x minus 7 equals 12y. Well, these are kind of scrambled up too, so let's get them into standard form, where we have standard form is like ax plus by equals c, where we have our variables both on one side and then the constant term on the other side. So for the first equation, I would subtract that 9y over to the other side. So we can rewrite it as 2x minus 9y equals positive 4. And then our second equation, let's add the 7 over and then subtract the 12y over. So it should be 3x minus 12y equals positive 7. All right, so first we had to rearrange things. Now let's try to get it into a situation where we're able to eliminate one of the variables when we add them together. So for our x's, we have a 2 and a 3. For our y's, we have a negative 9 and a negative 12. So it looks like we'll have to multiply each equation by some number in order to make the numbers opposite for one of the variables. So I'm going to focus on the x terms, these two. I want those coefficients to be the same number. So I'll even write that out here. We want the coefficients of x to be the same number but opposite in sign. Meaning one is positive and one is negative. So I want to multiply the top equation by something and the bottom equation by something else. So it's kind of in a similar style of, say, like getting a common denominator for a fraction, finding some least common multiple. And sometimes you just take the first term and multiply by the number for the second term and vice versa. So I'll show you what I mean by that. Like I have a 2x here and a 3x here. Well, if I multiply this first equation by 3, that will give me a 6x. And then if I multiply the second equation, to make the 3 equal to 6, I multiply it by 2. And I want it to be negative so that they will cancel out. So let's multiply the second equation by negative 2. So really I'm taking the number from the second equation and multiplying it on the first one. And I'm taking the number from the first equation and multiplying it on the second one. That will force the number to be the same. And then I make one of them negative. So I'm choosing a negative 2 so that one will be positive and one will be negative. So on my first equation, multiplying everything by positive 3, that will give me 6x minus 27y equals 12. Just multiplied each term by positive 3. For the second equation, I'll multiply by negative 2. So my first term will be negative 6x, then plus 24y, equals negative 14. So just multiplied each of these by negative 2. Now notice we have 6x and minus 6x. That's what we want. The same number and opposite in sign. So that when we add them together, our x terms will be eliminated. We'll have 0x. Then negative 27y plus 24 will leave minus 3y. And then 12 plus negative 14 will leave a negative 2. So we get negative 3y equals negative 2. Then let's divide both sides by negative 3. So the negatives will cancel because we have a negative divided by another negative, and we'll get positive 2/3 as the result. So we got a fraction which is slightly annoying, but it'll be okay. So y equals 2/3. So let's take this number and plug it in to one of the original equations. So let's just take this first one again. So I have 2x minus 9y equals positive 4. So let's plug in 2/3 for y. So 2x minus 9 times 2/3 equals 4. Let's see, we can view that 9 as 9 over 1, and 3 goes into 9 3 times. So really it's like a 3 times 2. So we'll have 2x minus 6 equals 4. Add the 6 over, so 2x will equal positive 10. And then divide both sides by 2. So we get a nice positive 5. So our solution point will be, I'll just stick it right here. The point x is 5, y is 2/3. So this one was the most involved we've seen so far. We first rewrote our two equations into standard form. I guess I should write that one over here. So we started with those two kind of messy equations, rewrote them into standard form in order to see them properly. And then here we had to multiply each equation by some number in order to get this situation here where we're able to eliminate one of the variables whenever we add them together. And then from there, we're following our process as above. We solve for one of the variables and then plug it into one of our original equations to solve for our final variable. So I think they give us a little series of steps here. Yeah, and my numbering might be a little bit different. So this is coming from the textbook. So step 1, oh, it might follow pretty nicely. Write each equation in standard form. So that's what we did. Then step 2, we determine which variable to eliminate. And it says, if necessary, multiply one or both of the equations by a number so that the coefficients of the variable to be eliminated are negatives of one another, meaning they're opposite signs and they're the same value. Then step 3, add the equations and solve for the remaining variable. Step 4, substitute the value found in step 3 into either of the original equations to solve for the other variable. And they add a 5th step of just checking your solution in each of the original equations. So we could go back and plug in 5 and 2/3 into these original statements and make sure that they produce something that makes sense, that they produce a real solution. And if you recall from working with solutions of linear equations and systems previously, there's a couple special cases that we might run into. We could either have a situation where the two lines that we're solving for, remember that these represent two lines in space. So what we've seen with the past three examples is two lines that intersect at some point. That's what we're calling the solution to the system. But we saw previously we could have like parallel lines that never intersect each other. In that case, we said there was no solution. Or the two lines could actually be the same line. It's like the same line just expressed in two different ways. In that case, we said we had infinitely many solutions, or every single point on the line was a solution of the system, because they're describing the same line. So let's see how those two special cases show up in this form as we're solving via elimination. So let's start this in the same way as before. We have, let me rewrite them out here. We have 4y equals 10x plus 3 and 6y minus 15x equals negative 8. So first I'll put these both in standard form. For the first one, I'll subtract that 10x over to the other side. So that will give me negative 10x plus 4y equals positive 3. And then for the second equation, I'm just going to swap the positions of the x and y term. I'll put the minus 15x first, plus 6y, this will equal negative 8. All right, so what should we do? Let's focus on a variable to eliminate. This time I want to focus on the y's because I have 4 and 6. I know if I multiply 4 by 3, I'll get 12. And if I multiply 6 times 2, I'll also get 12. So thinking of a least common multiple. So let's multiply the first equation by a positive 3. And let's multiply the second equation by a negative 2. So that will give me a negative 12 here and a positive 12 here. So I'll be able to eliminate the y variable. All right, so let's do that. Let's multiply every term in the first equation by positive 3. So negative 10 times 3 is negative 30. So negative 30x, then plus 12y equals positive 9. And then the second equation, multiplying by negative 2, negative 15 times negative 2 is positive 30x. 6 times negative 2 is negative 12y. And then negative 8 times negative 2 is positive 16. So notice what happens now when we add these two equations together. Notice both of the variables are going to be eliminated. We have negative 30x plus 30x, that'll be 0x. And then 12y minus 12y, 0y. So we end up with just 0 on the left side. And then 9 plus 16 is 25 on the right side. We get some false statement. Something that is not true. So that means there'll be no solution to this system. And then there's a technical term that was introduced previously for a system that has no solution. It's inconsistent. You can see like an inconsistent statement. 0 is not equal to 25. So no solution. And to use like set notation, we say it's the empty set, the set with nothing in it. So if you're going about the elimination method and you end up with a situation like this, some false statement, you can stop there and just say there's no solution. So let's see our next example. We'll see our other special case. So let me write these out. We have 12x minus 18y equals 9. Our second equation is y equals 2/3 x minus 1/2. So the first equation is already in standard form, so that's good. 12x minus 18y equals 9. And then our second equation, let's subtract that 2/3 x over. So it will appear as minus 2/3 x plus y equals negative 1/2. All right, now let's choose a variable to eliminate. If you see that one equation has a variable like on its own with just 1 as its coefficient, that's usually a good one to multiply by because we can turn that into anything pretty easily. Like I see I have negative 18y here. So if I just multiply the second equation by positive 18, we will be able to eliminate the y's. So let's do that. I'll multiply this equation by 18. So our first equation will remain unchanged, 12x minus 18y equals 9. Now let's multiply that second equation by 18. The first one is negative 2/3. Maybe I'll do that on the side over here. Negative 2/3 times 18 over 1. You can view it like this. 3 goes into 18 6 times. So negative 2 times positive 6 is negative 12. So sometimes it's worth doing the fraction stuff on the side. So that gives me a negative 12x plus 18y, multiplying that y by 18. And then 18 times negative 1/2, that's like dividing it by 2, and it picks up the negative, so this will become negative 9. So notice what happens here. Everything became the opposite of the first equation. So when we add this together, 12x minus 12x is 0, negative 18y plus 18y. Oh, this should be 18, not 8. Let's rewrite that. Plus 18y, that'll become 0. So we have 0 on the left side, and then on the right side, 9 minus 9 is also 0. So this is a true statement, but our variables have both eliminated each other. So we end up here. This was different from our previous situation where we got a false statement. If you get something like this, like something equals itself, 0 equals 0, this is a case where there's an infinite number of solutions. They're actually the same line. If we had multiplied this by positive 18, we would get the same equation as the first one. So in order to describe all possible solutions, we used the set builder notation. So the set of all points x comma y such that, and then we can stick one of these equations such that y equals 2/3 x minus 1/2. So all solutions to one of these lines will be a solution to the system. Another way of saying that is every point on this line is a solution. Every point is a point of intersection because they are the same line. That's another way to say that too. So these were our two special cases. As we're solving, if we get some situation like this, we get some false statement, 0 equals 25, not true, then the result is no solution. Or in a similar way, if we get something like this where the variables cancel out but it's a true statement, then there's infinitely many solutions. Otherwise, everything will work out fine and we get just a single solution, a single point of intersection. All right, let's see one more suggested technique. This is titled Using the Elimination Method Twice to Solve a System. So let's see what they mean by that. So we'll start out the same. Let me write out the system. I have 5x minus 6y equals 2. And then 9x plus 4y equals negative 3. So let's see. I see the 6 and the 4 again. I have negative 6y and positive 4y. So their least common multiple is 12. If I multiply this top equation by 2, that will give me a negative 12y. And then if I multiply the bottom equation by 3, that will give me a positive 12y. So we'll be able to eliminate the y's. So let's do that. Our first equation, multiplying everything by 2. 5 times 2 is 10, so I'll get 10x minus 12y equals 4. And for our second equation, multiplying everything by 3, 9 times 3 is 27x. 4 times 3 is positive 12. And negative 3 times positive 3 is negative 9. So now let's add these together. 10x plus 27x will be 37x. Our y's will cancel, which is what we wanted. Negative 12y plus 12y is 0y. So that gets eliminated. And then 4 minus 9 is negative 5. So then let's divide both sides by 37. So x will equal negative 5 over 37. So we get one part of our solution. Now, we could take this and go and plug it into one of these equations, but we'll get some pretty messy fractions. We will still get a solution, so there's nothing inherently wrong with that. But if we want to maybe avoid plugging in this weird fraction, we can just try eliminating the y's this time. I'm sorry, eliminating the x's this time. Like we can start over and eliminate the other variable and solve for y. So let's try this out. Let me rewrite the two equations again. 5x minus 6y equals 2, and 9x plus 4y equals negative 3. So let's focus on eliminating the x's this time. So I'm just going to take the first equation and multiply it by 9 because I see the second equation has 9 for its x. And let's multiply it by a negative 9. So we'll get different signs. And then let's multiply the second equation by a positive 5. So I'm basically just taking the number from one equation and multiplying it on the other, and I choose one of them to be negative. So let's see what that will give us. If I take negative 9 and multiply every term on the first equation, negative 9 times 5 is negative 45. So we'll get negative 45x. Negative 9 times negative 6, double negative, it'll become positive. And then 9 times 6 is 54. So I get 54y equals negative 9 times 2 is negative 18. Now for the second equation, we're multiplying everything by positive 5. 9 times 5 is positive 45. 5 times 4 is 20, so plus 20y. And then 5 times negative 3 is negative 15. So we have positive 45x and, or negative 45x and positive 45x. So that's what we want. So when these add together, our x's will cancel, and we'll be able to solve for y. So we'll get 0x, then we have 54y plus 20y, so that should be 74y, and then negative 18 minus 15 will give us negative 33. Then let's divide both sides by 74. So y will equal negative 33 divided by positive 74. So that's what we should get if we went and plugged in this x value to one of the equations. So we would have had some messy fractions there. So it's a way to, it's like a secondary path that we can take to avoid working with more complicated fractions. So our solution will be the coordinate point negative 5 over 37, that was our x value, and negative 33 over 74 for our y value. And so I just want to say again that we can solve this system with any method we want. We could try to solve it with substitution. We can solve it with elimination, where we take the previous answer, or the answer for one variable, and plug it into an original equation. Or we can solve with elimination twice like this and get our two different parts of our solution. And so there's, depending on the way that the question is set up, one process might be easier than another process. And you might have to just pick one and see how it's going, and you might want to backtrack and try a different method if it's becoming too complex. But you should arrive at the same result regardless of the method that you choose. The answer will be the answer regardless of how we get there. So we have some choice in the method, and we can be intentional and a little bit tricky to choose the method that will require the least amount of complication of us. All right, that's it for this section. So we described the elimination method, saw a couple different situations with that. We saw our two special cases of having no solution or infinitely many solutions, and then that special trick of using elimination twice to solve a complicated system where we might have to work with some messy fractions. All right, that's it for this video, and I'll see you next time.